Good morning. I'm Manuel Güdel, as you can see here, from the University of Vienna. I'm working in Heidelberg at the moment for a year. That's why you see this address as well. I'm coming from astrophysics, so I will actually talk about physics. Some of you are not in this field, but well, we need to talk about physics as well, right? I'll show you a few equations even, but I don't want to take you through a lot of math, of course. But just showing pictures would also not be it. You will see pictures like this one. But I want to give you some basics of why there are physical processes in the universe that form stars. So don't be really shy to look at these equations I show you. I will explain what they mean. It's important for you to see what forces act to make a star, to make a sun, to make a solar system. And I'm not going into modern simulations, complex things again, movies and whatnot. I'm trying to show you the very basic processes that are important for star formation and for disks before a planet forms. We'll not talk about planets today. Planets come tomorrow. Aurélie Krida will talk about the planet formation process that exactly follows what I'm going to discuss. Good, so these are the topics I'm planning to. It's a lot of things. I cannot go deep into any of these, but I'll talk a little bit about the interstellar medium because that's where it starts. That's a bit more for theory now, collapsing clouds and stability, because we have to start somewhere and see whether we have star formation or not. Talk about protostars, protoplanetary disks, then the T-Tauri stars, the first sort of solar-like stars that we see. A little bit of chemistry, structure and dynamics of disks, accretion and outbursts, and at the end, at some point, things disappear again, the disk goes away, and so I talk about disk winds and dispersal. Now, before I do that, we should not forget that we have a history. Astrobiology has history, and I'm taking you back more than 400 years now, and I would like to read this together with you just to remember that some ideas of what we are discussing today and at present are actually going back hundreds of years. They go back 2,500 years indeed. But let me quote somebody named Giordano Bruno. You may know about him. And what he said in his work reads about like this: there are countless suns and countless Earths, all rotating round their suns in exactly the same way as the 7 planets of our system. We see only the suns because they are the largest bodies and are luminous, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no worse, no less inhabited than our Earth. For it is utterly unreasonable to suppose that those teeming worlds, which are as magnificent as our own, perhaps more so, and which enjoyed fructifying rays of a sun just as we do, should be uninhabited. And finally, the unnumbered worlds in the universe are all similar in form and rank, and subject to the same forces and the same laws. This was said more than 400 years ago. The fate of this person was not very good, because what he claimed was not welcome at the time. But you see here actually he talks about stars being suns. That was an idea that was not fundamentally accepted at the time. He talks about planets surrounding every star in the universe. We know that actually only for a short while so far. We know now there are more planets in the universe than stars. On average, every star has at least 1 planet. That's a very new finding. Of course, he didn't know, but he anticipated that something like this will be found. About life in the universe on the planets, well, we don't know yet. We'll see whether he was right or not. Maybe soon. We have the means now to, for example, with the James Webb Space Telescope, we have the means to look at planets and see whether there are traces that indicate the presence of life. And the last one is actually not less important, that comment about universal law. That was also not accepted at the time, namely that the stars, the sun, the moon, follow the same laws as those that take place, those that hold on the Earth. So again, these are very important words in one short text. If you are interested in such things, you can also go back another 2,000 years to find Democritus, who made also statements along those lines. So there's a long past really now of our science. But let me get back to now, to what we want to discuss today. Before I start, I show you 3 theses that I sort of think that are interesting to discuss. We're not going to discuss them, but we are going to vote on them. So, thesis number 1. Stars form inevitably because gravitation contracts gas in the universe. You see here a galaxy of 100 billion stars. There are lots of stars, as you can see. You can't even distinguish any of them. It's just a shining blob of material. The second thesis is stars form everywhere and abundantly across the universe. And the third thesis is star formation is important. Now, what do you think about that? What is your opinion? You need to have opinions, because we cannot prove everything. We should start with opinions and then see what we want to do with them. So what is your opinion about number 1? Now I'm asking you. Do you think stars form inevitably because gravitation contracts and so? Who thinks this is right? Hands up. Nobody. Should we not talk about this? Okay. Okay, sort of 30%.
Physics, so I'm sorry. I cannot presume.
Okay, no problem. Maybe 30%. Okay, that's interesting. Stars form everywhere and abundantly across the universe. Who thinks this is right? Not many. So I should have asked before. Who thinks it's not correct? There are many people without opinions.
I don't entirely agree on the other word.
But the last one. Star formation is important. Oh, I'm happy. I'm happy about this because that's the purpose to be here for myself. So if you said it's not important, I should probably stop my lecture and go on. Right? Good. So here's my opinion, and it's my personal opinion. Stars form inevitably because gravitation contracts gas in the universe. I don't think this is correct. It's not fundamentally correct. It's in a part of it, but it's not automatic or anything. Stars form everywhere and abundantly across the universe. I also don't think this is correct. And I hope I can convince you that there's something with this. Oh yes, star formation is important. I absolutely agree with you. Good. So, for those who are not in the field, let me bring you to the same page by just looking, I need to sort of define a few things so that you know what I'm talking about, really. This is a night sky image. I'm turning it around. This is now a whole sky image, and of course you see what it is. It's a Milky Way band on the sky. What is the Milky Way? Well, that's what I want to briefly show you. This is now going around us 360 degrees. The whole sky is shown here, and you see this wonderful Milky Way. What is it? So if we had a chance, we're somehow sitting here where we are in this lecture room, and let's take a rocket and move vertically away from outside. We look from outside and look down on what we see here, and then what happens would be this. This is a galaxy, obviously. A wonderful spiral galaxy, and that's actually where we sit. We sit inside this sort of flattish spiral galaxy. So our sun would be about here. It's halfway out. It's between some spiral arms. And such a galaxy is made of something like 100 billion stars. It's a huge number of stars. So that's just to show you a little bit where we are that's our environment. There are another 100 billion galaxies in the universe. It's a huge number of stars. Now, before I really go into the topic, I also should show you, because what you just saw is a huge structure. So let us talk a little bit about distances, where we are in the universe and what it means to go to new other objects. this is probably familiar to everybody. That's the solar system. You see the planets. The orbits are to scale. Here, the inner solar system from Mercury, Venus, Earth, and Mars. And then the continuation here, Jupiter, Saturn, Uranus, and Neptune. That's sort of showing the orbits of the planets. Now, to make things a bit more convenient for astronomers, there is a definition of a distance which is called an astronomical unit. And that's the average distance of the Earth from the Sun, 150 million kilometers. So whenever I use the expression astronomical unit, that's it. I don't want to talk about centimeters all the time, because, or meters, we conventionally use centimeters in astrophysics, but that would be a huge number. So 1 astronomical unit, and compared to that, if you go out to Neptune's orbit, it's 30 astronomical units. So that's about the size of our solar system. Just to, please do memorize this a little bit. Astronomical unit, that's a convenient measure for the solar system. Now if you go to the stellar environment, here are the nearest stars. That's a projection, a pseudo 3D projection here of the nearest stars to the Sun. You see the Sun in the center. Some of these stars you may know. Sirius, for example, is actually not far away. Alpha Centauri, Proxima Centauri, you should have heard these names, I would assume. And many others you will not recognize. And here we also have a convenient measure of distance. The usual the measure we use. It's not a light year, but something called parsec. I don't want to go into discussing what a parsec really is, but it's a length scale of about 3 light years. And that length scale of a parsec is convenient because it's actually about the distance between any 2 stars in the solar environment. You see the nearest star, Proxima Centauri, is actually 1.3 parsecs away. So whenever I use parsec, this is a scale between stars typically. Now, how big is it? It's 200,000 times larger than 1 astronomical unit. Massively more. The nearest star is much, much further away than Neptune. So we measure here in orders of 10 to the 5 times the distance between planets. And finally, I showed that already, where is our Sun? Our Sun is about 8,300 parsecs away from the galactic center. We don't need this, but I just for completeness wanted to show you. Good. So let's go into the topic of star formation and first look at what we have available. What is the material? You see again a beautiful galaxy here on the left. Spirals, our Sun somewhere. And when you look more carefully and you look in fact in our Milky Way, you see a lot of structure that's not stars. You see gases, like here. You see cloudy material, like all these dark patches here. We call them, in fact, clouds. Interstellar clouds. Maybe gas. Here it's also gas, but you see these dark features. You can already predict, in fact, that it's not only gas here. There's dust, there's solid material, because the darkness of these clouds has to do with absorption and scattering of light of the background objects by dust, not the gas. It's really also dust. And this is an area of the sky that you may be familiar with, because these are the Pleiades. Probably seen them in the night sky, can see them by eye. And there is an area here next to the Pleiades that is a lot of dark clouds. So why are you interested in them? So let's see. This is sort of a classification of clouds, or of the interstellar medium. It's not only clouds, it's the extended interstellar medium. This is a table. I don't want to read the table, but just for your information what we have. We have very different types of gases out there. We have molecules. Clouds are made of molecules. And when I talk about molecules, it's mostly hydrogen and helium as well. Because that's the cosmic composition of the original gas and matter we have, mostly hydrogen, helium, and then a few other things. I'll come back to that. We have atoms as well. Cold atoms, warm atoms, and even ionized atoms. And then we have plasma, very hot gas. And these fill different volumes of the galaxy. And maybe, you know, I should really emphasize the molecular hydrogen clouds or gas. This is a very cold state of gas. It's 15 K. So very cold, 15 Kelvin. But it's very, sort of for us, it's a high density environment, 250 particles per cubic centimeter. That's not much. But for us, it is a relatively high density. And then we have all these other interstellar medium components. We have gas at 80, at 8,000 plus or minus, of course. These are just typical averages. And then up to 1,000,000 degrees. And you see also densities are very different. But what is important to remember is that the molecular gas, which is actually the gas that we are interested in star formation, makes only about 1% of the volume in a galaxy. So it's only little patches that consist of molecular gas. They're very cold, they're dense, but the mass they contain is 20% of the interstellar medium. It's very compact, and compact gas is, of course, the gas that we want to see to form stars. Very tenuous gas like this, has hardly anything in it, is not important for star formation. Although, in terms of volume, there's a lot of, it's a large fraction. Good. The hot gas, actually, just as a comment, is a bit of an unusual component. It's formed by supernovae that expand and fill bubbles, blow bubbles into the other interstellar medium. And also, molecular clouds, we'll see, gravitation is an important part of this. Now, what is the composition of this gas? Quite in general, it's true for all gas forms that I've mentioned now. Well, the composition is, well, first of all, it's gas, as I said. And I already mentioned there's also solids that we call dust. And in terms, on average, the composition is about 99% is gas. And of that, it's mostly hydrogen gas, 90% of those 99% hydrogen. There's helium, another 10%. And then all the other elements we know of, like oxygen, iron, sulfur, silicon, and whatnot, are only there in traces of order 10 to the -4 and less, a few times 10 to -4. So that's the material we have at our disposal. Dust, I say a little bit more later, is 1%. And these are the elements that do not like to be in a gas phase. They assemble to little solid pieces, as I said, called dust, micrometer size and less, and that's about 1%. Carbonates, graphite, whatever. So what is dust? Just to come to that point, dust is composed of so-called refractory elements, those that don't like to be in the gas phase. For example, iron, magnesium, silicon, carbon, sulfur, and so on. That's 1%. In the most simple way, you can think of a dust grain as something of nanometer to micrometer size. It's made of a solid core, usually, as I already mentioned, silicate, carbonate, whatever. And then there may be, in some instances, you may have ice mantles around them, because some of the gas may actually stick to the dust and condense on dust grains and form ice mantles, because it's too cold for these gases. Not all of them, and it depends on the conditions. Ices are in cold regions. The temperature need for ices is typically something like 20 to 150 K, depends on which molecule you're looking at, carbon monoxide or water also. Water condenses at about 150 K. If you're colder than that, you form ice mantles around dust. Dust has its distribution in sizes. There are not the same number of dust grains at every size. You get typically a lot of small dust, micrometers, nanometer sized even. You get few grains that are larger, like micrometer. And there's a distribution that says that the number of grains per radius interval is something like goes with r to the -3.5. That's a very steep distribution, so a lot of small dust, not so much large dust. Dust is the material that we need to form Earth-like planets in the end. So that's a discussion for tomorrow. Real dust is, of course, not spherical balls. It's much more complicated. You see an example here. We can collect dust from example, from comets, as has been done recently. This is an image of a relatively large dust grain. 1 micrometer is this bar here, so there's several micrometers in size. These things are very complex, fluffy, irregular, fractal structure, whatnot. So if you deal with this, it's becoming really complicated. So it has to make approximations. Good, and that's how you see the interstellar medium. You see the dust, actually. This is a historical image taken by Barnard, 1927, almost 100 years ago. Again, this is actually the same thing that I showed you a little bit earlier. The Pleiades would be out here, very close to this image. What you see are these dark patches across the image, some sort of filamentary structure here and here. And at the time, researchers were collecting and collecting a catalog of clouds in the sky and mapping the sky. And they found many, many of these regions across the entire sky. What you see here is, in fact, the action of dust. It's not the gas that you see here, it's the action of dust. Once you have a high concentration of dust grains, they tend to absorb the light that comes from behind, from other stars, and also scatter the light away from the line of sight, so you don't see the stars behind. So these are really dense clouds that are not transparent to optical light. So they appear dark. But now I show you a superposition of a modern image in color, and that shows where gas is. Now this gas has been recorded at millimeter wavelength with a radio telescope that shows you carbon monoxide, not hydrogen. Because carbon monoxide is easier to observe. And you see that there is an exact match between the dark areas, where there is dust, and see the gas in CO. It's exactly the same place. So where you find dust, you find gas. They always come together. And in a typical ratio that I mentioned already, 100 to 1, approximately. And it's these regions that form stars, because they're dense, there's a lot of material there, and they're cool. Another example here, again, you see in the diagonal feature here, you hardly see it actually, it's dark, right? That's an optical image of a filament, also in the same star formation region, in Taurus. And now we switch to infrared. Now I'm not going to show you where the gas is, I'm just switching to infrared, or in fact I switched to millimeter wavelength, taken by radio telescopes. And what you see is this. Now you see, in fact, radiation that comes from the dust, because the dust is not at 0 K. It has a temperature. And whatever has a temperature, like in this room, radiates infrared or millimeter wavelength because of its temperature. There's all this radiation. And so you see these things become bright if you go to longer wavelengths. So again, you actually see at least 2 objects here that may be forming stars. You see these condensations here, these bright spots. And so that's where it begins. And that's what we want to discuss more today. Also, the structure of these clouds is very often filamentary, very long stretches of gas and dust. These are 2 examples, so-called Horsehead Nebula. You may know it. It's very famous, and it looks a bit like a horse head, of course. This is an optical image. Don't care about this red background. This is ionized gas that radiates, that emits in this color, indeed, in the optical range. But the foreground cloud, dust and gas, is not transparent. And if you go to the infrared wavelength, this is now an infrared picture, you see that this is becoming transparent. Now, why is that? You don't only see the radiation coming from the dust itself, but you see it's getting transparent. And that happens because the wavelength of the light, of the infrared light, is larger than the dust grains. We are talking about micrometers here, but the dust is mostly 100 nanometers or less. So you begin to see through the clouds with wavelengths that are larger than the dust. So that's another advantage for going into the infrared wavelength range. A few more, well, actually it's the same again. This is a modern image now of the Taurus cloud, the cloud that we saw before in the constellation of Taurus. This is the whole thing now, but now it's taken in the infrared, in the far infrared. And you see again the emission that comes from the dust. It's no longer dark. Here it's actually all bright clouds. And that's a typical example of a large cloud complex. There are many, many things going on here, many stars forming actually. It's a total mass is 10 to the 4th solar masses. It has a diameter of, now comes the unit, 10 to 20 parsecs. So it's a distance, many times the distance between typically two stars in the solar neighborhood. It contains a lot of mass, as I already said, and this region is forming stars. It forms predominantly low mass stars. And when I say low mass, I mean masses of the Sun and less, about the solar mass less. These are relatively small stars. In contrast, here is a giant molecular cloud. This fills almost the constellation of Orion that you see in the night sky. It's very prominent. You don't see these clouds. You may know the Orion Nebula, which is a very small shining cloud somewhere here. But the molecular cloud is much larger. Now we're talking about 200,000 solar masses that participate in star formation, many stars being formed here. The diameter is 90 parsecs now, much, much larger than what we had above. And here also stars with masses of 5, 10, 20, 40 solar masses, very huge stars, are also formed in such clouds. You see clumpy structure everywhere. It's not a homogeneous distribution of gas. You see all these little cloudlets. And this is the subject of the discussion. Indeed, here is one of them. It's not in the same star formation region, but that is now a really smaller cloud. And these are interesting for star formation. Again, this is an optical image. You see already there's something funny going on here. You see a dark cloud because it's not transparent. You see dust filtering, dust basically making cloud taking away the light of the background stars. You see something funny here, this linear feature. I come to that, but let's not focus on this at the moment. You don't see what's inside, right? It's just dark. But that's because it's an optical image. Now we go to longer wavelengths. As I said already, maybe we can make this transparent, and indeed we do. This is now an image taken at millimeter wavelengths, and you suddenly see more of these features. They're inside the cloud and behind the cloud. And this part here just happens to stick out of the cloud, and it's visible from the outside. But most of this stuff is in the cloud. And this is a clear indication that we have a star forming right here in the middle. And what you see here are outflows of gas. A forming star, I'll come back to that later. Forming star ejects mass. It of course collects mass because it needs to grow, but at the same time it ejects mass as well, usually along the polar directions, north and south. So these are such features, many of them. But the protostars, as we call them, the protostars are sitting somewhere in the center here, and you see this cloud is forming a star. Now comes the theory part. I'm sorry, but I need to torture you a little bit with a couple of equations. I'm not going to make derivations here. That would not be appropriate. But to now understand what's going on, I need to take you through a few equations. I will explain every term that we have here. And going back into your studies, you will remember some of them, maybe all of them. Good. So sorry if there's some of this is maybe a bit tricky, but let's try. If you want to describe a gas cloud and its motion, you need something that's called the equation of motion. You need to see what the forces are doing, the force balance. There are forces acting against each other. I'm sure you have written many of such equations, maybe not as complicated as this one, but it's not so complicated indeed. Let's just collect all the forces that act in a molecular cloud, in one of these little clouds that we saw. Now, you have a term that's mass. This is actually density. We do it per volume. Mass times acceleration. That's a force, right? F equals m times a, it's usually called. Mass times acceleration. So that's a force. That's the inertia of an accelerated mass. And then you have to collect the forces on the other side. What forces act? Well, if you have a warm cloud at some temperature, you have pressure acting. It's not the pressure itself, it's a change of pressure. If you look in meteorology, you have high pressure regions somewhere and low pressure regions, and that makes all the dynamics, you know. From high pressure to low pressure, gas wants to go to lower pressure. So there's a force acting there. And the force that acts has to do with the gradient, the change of pressure over distance. It's just a gradient. And this gradient is symbolized with this inverted triangle. You should be familiar with this nabla operator, are you? From calculus. So if I'm too simple, let me know, right? It's just repetition for those who may not be very familiar with this. So we have the gradient of pressure. It's a negative sign here. Pressure goes from high pressure to low pressure. The force, you know, acts against the increase of pressure. You increase the pressure in one direction, the force points to the other direction. Gravitation is a force. Every mass is gravitation. And this is written here in a somewhat general way. You need mass and you need the potential, which is psi, and the gradient of the potential is the force. We don't need this anymore later. So nabla psi, you can formulate gravitational attraction or by this expression. So that's a gravitational force. On a mass element, well, it's mass per volume. And then we have magnetic fields, perhaps. And if you have charged particles, like electrons or ions, they circle around the magnetic fields, and then you have a Lorentz force. And that is important here as well, as we will see. The Lorentz force is formulated as the cross product of a current, so it's charges per square centimeter per second, current density, times the magnetic field strength, 1/c. So we are not going to show you what I'm doing with this equation, but there's a lot of manipulation you can do with this. Most importantly, you can integrate over a volume, and then you do some other manipulations. And what you get eventually is this very simple equation. For a cloud that should not collapse now, it should be in equilibrium, all the forces balance each other. You get this expression. This is called the virial theorem. And it's true for many situations where you have a stable situation in a system that is basically separated from its environment. A gas ball, for example, that should form a star. Now, what does it say? It's actually an equation between energies. It says, and that's all coming from the equation that we had before, it says that 2 times the kinetic energy from motion plus 2 times the thermal energy that comes from temperature, plus the potential energy that comes from gravitation, plus the magnetic energy, that's actually due to the Lorentz forces, equals 0. They balance each other. As long as our cloud is stable, they should balance. Now, a few expressions, just, you know, for curiosity, what are these expressions really? You know, kinetic energy is mass times velocity squared divided by 2. This is random motion in a cloud. You can have kinetic energy of substructures inside a cloud. The thermal energy is essentially Boltzmann constant times temperature and then the total mass of the cloud. And there is a normalization with the proton mass, and the mu is about 2.3, it says, for the typical mass of a single particle, a molecule or an atom. The average is about 2.3 times the proton. That's typical for molecular cloud gas. So this is the thermal energy. The gravitational energy comes from the self-attraction. So gravitational force, if you have a body that is away from the gravitational center, it has gravitational energy. That's potential energy. And if you calculate this for a sphere, a homogeneous sphere, you get an expression that basically has an m squared. That's the mass of the cloud squared divided by its radius. A very simple expressions. And for the magnetic field, it turns out that magnetic energy is B squared times the volume, essentially, and some factors. Good. Now, again, I will not actually need these expressions. It's just to remind you how they're connected to basic parameters like temperature or mass. But I will use this equation again, this very simple equation that the sum of energies is 0. Now, the magic here is that all these terms turn out to be positive. Kinetic energy is always positive. You can see that from V squared. Thermal energy is positive. The magnetic energy is positive, you have B squared. But the potential energy is always negative. If you have a body away from the sun, for example, far away at infinity, it has no potential energy relative to the sun. The closer it comes, the more potential energy in an absolute term it has, but it's negative. It drops. Right? If you lift somebody away from the Earth, you increase its potential energy, but the normalization is such that at infinity it's 0, and then it drops as you come closer to the Earth. So what we actually need here is, in this equilibrium situation, I'm talking only about equilibrium at the moment, this is 0 here, is that somehow this one negative energy term, the potential energy of a cloud, must be balanced by all the others. Otherwise you have no stability. And that's the way we'll look at stability now in the next slides. So if we do not manage to fulfill this equation at the top here, we'll have a collapsing cloud. And we'll see how we do that. Now, from observations, this is simply observations, there's nothing theoretical here. We know that the kinetic energy as measured in a typical cloud, all the random motions of substructures in the cloud are actually of order of magnitude in absolute terms, similar to the potential energy. The same is true for the magnetic field terms. You can measure magnetic fields in clouds. So this is also order of magnitude. It's not exactly the same, but order of magnitude. You can also say for the very giant molecular clouds, the thermal energy is not important. These clouds are not supported by pressure. So that term falls away. Good. Let's see, here is one more of these clouds, a different one. It's not the same as showed before. It also has something in the middle here that's not seen in the optical light. This is actually an optical image. But it's seen as with radio wavelengths, you can penetrate through the cloud. You can see this protostar here in the middle. These structures are simply from observations. They have densities of about, number shown here, diameters of about 1/10 of a parsec. Masses, a few solar masses. That seems to be ideal to form a sun, right? There's more than enough material. Temperatures are very low, 10 K, a little bit of magnetic fields. They may rotate as well. And such things are called dense cores. There are many of them. This is a typical dense core. And here, gravitation is really important, self-gravity, because there's enough mass to really pull the cloud together. But there's also something different from what I showed you on the previous slide. Now, in these small structures, 2 times the thermal energy is actually of order of minus the potential energy. So the equilibrium in these little clouds is indeed between thermal pressure and gravitational pull. These may be thermally supported simply because there's a pressure gradient. In fact, there's also magnetic fields, but come to that a bit later. So the question is, now we have such a cloud, and we saw they may be in equilibrium. The equation of energies, says all the energies together are 0. So how do we actually make a star now? The cloud is stable. We have many of these in the sky. We can see them. Nothing happens. Let's see whether we can make them unstable. This is a sort of a simple experiment drawn on in a PowerPoint slide. We take a universe that's full of gas, homogeneously distributed, same density, same temperature everywhere. And now we make a little bit of a perturbation. We make a wave. We let a plane wave into the gas, and let's see how the waves propagate. So this is a perturbation of the gas. See it here linearly. Wave comes in, and you see pressure bumps and pressure valleys, naturally, like in every wave. Now the question is, what happens with this? In the pressure bumps, you have more concentration of gas. That makes more pressure. So that pressure would like to expand the pressure bumps again. So the wave would go away. It will be dampened. On the other hand, you have self-gravity. You have more mass pushed together in this wave. And so maybe self-gravitation tries to, collapse them. Now, what's true? Who wins? And that's not a trivial question, because actually pressure could win or gravitation could win. And we have to analyze the situation. So what happens as I said, what's happening is either the wave continues to propagate and nothing happens, or the self-gravity is so strong in the pressure bumps that the pressure bumps collapse and make sheets, very thin sheets. These are our one-dimensional stars in the end. So this is a thought experiment, but indeed it's very well known as an analysis that was proposed by Jeans about 100 years ago. And the whole, as I will show you, this is a criterion. We'll derive a criterion that's called the Jeans mass, Jeans criterion. So what we can do to find whether or not the cloud collapses is, well, we just forcefully violate the virial theorem. We now say that the potential energy should be greater than 2 times the thermal energy. And then see what happens. We know the term, we have seen what thermal energy and what potential energy is. I showed you these little formulae before. So we plug them in and say, well, let's this be larger than the thermal energy, so 2 times the thermal energy. What's coming out, don't need to go into any details, this is very trivial. You just need to take the 2 expressions I showed you, solve for m, and you see that the cloud mass must simply be greater than this expression that has temperature to the 3/2 and density to 1/2, and in 1 over rho to the 1/2. That's all. If any cloud like this one or a substructure is larger than this expression, it collapses. And if it's not, it doesn't collapse. You can perturb it, but then it just oscillates and it dampens and it stays. This is called the Jeans mass, this criterion. It's not the mass of the cloud. It's a formula. It's a quantity. And you have to compare the mass of your cloud with this expression, with its own Jeans mass, and then you see whether the cloud can collapse or not. If you look in real in observations, you find indeed that the cloud mass needed for a collapse is a few solar masses. That's ideal, because that's what we need, right? That's what we need to form a star. So it happens to be really matching well with the expectation. There's a more detailed model. I may mention that every now and then. If you do a bit more like a 3D analysis, you get to the Bonner-Ebert mass, as it's called. It's essentially the same thing. And you can even calculate the structure of your cloud that begins to collapse. It's a bit denser inside, it's a bit less density outside. Good. That was the main math for this subsection. But anyway, let's continue. We have another problem to solve, because some of these clouds rotate. And everything rotates in the universe. You cannot avoid this. But rotation seems to be unimportant once the cloud sits out there. They're actually not rotating very rapidly. But you can imagine what happens if you start them, spin them up. The centrifugal forces, so we have to be careful there as well. There's another energy term. That's the energy that is in rotation, because we have a motion and we have an energy term from rotation. But as I said, it turns out that the rotational energy is again really very small compared to the gravitational energy. So we can ignore it. However, The problem is once we want to actually collapse this cloud, and what happens, well, I shouldn't actually even discuss it at length, you know that, but let's just watch. This is an ice skater. She holds the world record apparently in spinning. You see what she does, and you know. Now, what has she done to do this? Again, most of you know that, you know, let's not make a long story. Well, what she does, you see her arms and one leg is being you know, spread. And then she pulls the arms and the leg, and the rotation increases. This is basically the effect of angular momentum conservation. That happens, of course, easily, you know. The shorter the distance from a mass, an element of mass, is to your rotation axis, the more you can spin up. Good. So what's in this? Again, a little math, because this is, you know, math that you had, you know. A definition of angular momentum, it's essentially in a circular motion, the mass of a body, its velocity along the orbit times the radius. You can transform this a bit if you define the angular velocity of a body in circular motion as the velocity is equals to omega times r. That's the angular velocity, is the radius. Plug that in, you get this expression. This is conserved unless you apply torques to the body. Otherwise, it has to be conserved. So this expression is constant if you don't make external changes. There's something like the centrifugal force that, again, I assume that you remember. It's in orbit, in a circular orbit. Centrifugal force is mass times v squared, the velocity squared over r. You can plug this constant value, plug that in, and you see that the centrifugal force goes with 1 over r to the third power. So if r becomes small, if you pull your arms closer to your body, then the centrifugal force, if you're rotating, goes up massively, like 1 to the r to the third power. You know, so you change the radius by 2, the force increases by a factor of 8. That's a very strong dependence. Now the gravitational force also increases. A more compact body has more self-gravitation, but that goes with 1 over r squared from Newton's law. So the centrifugal force grows more rapidly than the gravitational force. So if you make a body smaller, a cloud, a rotating cloud, the centrifugal force grows faster than the gravitational force. And that means at some point we can no longer collapse, because the force the gravitational force, the centrifugal force is just too big. So at some point our collapse has to stop. Let's do an experiment again. Let's just plug in numbers. Let's start with the core as we saw it in the pictures, 0.1 parsec. Should we have a rotation period of 200 million years? Why 200 million years? This is a very conservative estimate. The galaxy rotates, our galaxy rotates about 200 million years around its axis. So let's assume all these little mass elements go with it and also have a rotation period of 200 million years. It can be a bit faster than that, but anyway, this is a conservative limit. It should have order of magnitude such a rotation period. So this element also rotates in 200 million years, so 1 solar mass. And now we want to contract this to a sun, our own sun, which has a radius, which is very well known. And then what I showed in the previous slide, the angular momentum, which is proportional to r squared over the period, should be conserved. So you have an easy way to calculate what's the missing parameter? The rotation of the sun after the contraction of the cloud. So what would the rotation of the sun, you plug in these numbers here, r squared over p is constant, and you find the rotation period of the sun as it should be from a collapsing cloud. What you find is 350 seconds for the rotation of the sun instead of 25 days. That's a bit too much, right? I mean, it doesn't agree with the observations. But in fact, the centrifugal force at the surface of the sun would be 850 times more than the gravitational force. So the sun would actually fly apart. That's not good. So we have to stop that collapse at some point because it doesn't work. We do not form stars. Just a few numbers. You know, these are in the units that we're using in CGS units, grams square centimeters per second. If you have a dense core, those little gas clouds, they have a, you know, something like 7 times 10 to 52, these units. If you take the sun, it's only 10 to 49. So it doesn't really work, right? You cannot conserve angular momentum. There's something funny. Jupiter's orbit has also angular momentum. Not Jupiter as a body, but its orbit. Jupiter in its orbit has 2 times 10 to 50 units, 20 times more than the rotating sun. So maybe a trick actually to do something with this angular momentum is put it into a planetary system. And that's part of the solution indeed. It doesn't, you know, we need more, we need to take away more angular momentum at some point. Okay, this is a simulation that shows you how such a collapse could proceed. You see how complicated it really is. It's not a spherical cloud that collapses, but we will actually continue to talk about spherical clouds. But this is a simulation that shows you also what's going on in terms of angular momentum. You see how angular momentum, you know, builds up. There's some rotation here, and of course you can also, you know, just basically separate the clouds. One rotates this way, the other half rotates this way. You create regions with a lot of angular momentum and see how this evolves. You know, see these rotating pieces. And in fact here, there's so much angular momentum developing that you form 2 stars. You form a binary star. And that keeps some of the angular momentum in the orbit of the 2 stars around each other. That's a complexity, and I hope you agree that I'm not going to describe this complexity. We'll keep it much more simple. Because we have to. Otherwise, I will show you just simulations. So let's go back. There's something else we have forgotten, and we mentioned it already, were magnetic fields. So let's see what we have there. We can measure magnetic fields. The magnetic field strength here on Earth is something a little bit less than a Gauss. In sunspots on the sun, you measure 3,000 Gauss maximum. So these magnetic fields, they're everywhere in the universe. You find magnetic fields, and these clouds you find field strength of a few to a few tens of microgauss. So they're not very strong, but nevertheless they're important. And as I sort of mentioned already before, we find in these small clouds also that the magnetic energy is also similar to the potential energy, together with the thermal energy, which we already discussed. So indeed, it's not only the thermal pressure that may counteract the gravitational attraction, but also magnetic fields. They are equally important. That's an order of magnitude estimate here, of course. Now, that means that the magnetic fields, if they are strong enough, also prevent the cloud from collapsing. So we have to be careful to consider this as well. Now we know how to do it, of course. We'll take the virial theorem and violate it, right? Just take the magnetic pressure being larger than the gravitational expression. But let's first discuss a little bit what magnetic fields are doing to a gas. You know, you should know that, of course, but just repeating it. If you have, this is now again a spherical cloud, and you have magnetic fields, homogeneous magnetic field, all in one direction. And now let's assume we have some charged particles in this cloud. And in fact, molecular clouds, as cold as they are, they have ions and electrons, free ions, free electrons as well. And that's because they are slightly ionized by cosmic rays, very high energy particles that are everywhere in the universe from supernova remnants, created in supernova explosions. So there are ions and electrons, and they have to be attached because of their Lorentz force. They have to be attached to the magnetic fields. They cannot leave them. But they can slide along the magnetic fields. That's not a problem, but it cannot go vertical in vertical direction here. Perpendicular to field lines, that doesn't work. Good, so if we have plasmas, this is called, a gas of charged particles, then if we compress that gas, the ions are of course also compressed together with all the neutral gas. Then the field lines have to come with the ions and with the electrons because they cannot move away from their field lines. So they come together. That means all the field lines, which is an abstract concept for a magnetic field, they all come together as well. So it's the same number of field lines, if you will, that is still there in this compressed cloud. Because the particles, charged particles, will dictate this. Compression is all field lines stay in. But that means that the quantity that we call magnetic flux, which is simply the field strength times the area of a cross-section, is constant, cannot change, right? Now you remember, well, if the radius becomes smaller, then the field line will become stronger. The field lines are denser, packed together. They're denser in the compressed cloud. So the magnetic field seems to increase as the radius decreases. And you remember we had this B squared in the energy term. Magnetic energy goes with B squared. So the energy increases, magnetic energy, in a collapsing cloud. Good, again, let's apply this to what we can measure. A typical interstellar magnetic field strength is 10 microgauss, let's say. Can be more or less, but that's the order of magnitude. That's 10 to minus 9 Tesla. And now let's make an experiment as we did before. Let's take some cloud, 1 solar mass, 0.1 parsecs again, and let's collapse this to a sun. One sun, And we know that the magnetic field lines that collapse with the collapsing cloud end up in the sun because they cannot leave the cross-section. They're pulled together with the ions and the electrons, pulled together. So what happens? Well, I said the flux is conserved, B times R squared, magnetic field strength times the area. Then you can easily calculate this, we have all the numbers, and see what the magnetic field strength will be in this collapsed star. We go from this situation to this situation, magnetic field lines are pulled into the star. And the calculation is, of course, easy. B squared times R is constant, we have the numbers here, and you get a magnetic field strength in the sun of 2 times 10 to the 8 Gauss. That's an enormous magnetic field. What we measure in stars and in our sun is more like 3 kilogauss. So there's a problem here. Indeed, if you calculate the gradient of the magnetic, of the magnetic pressure from the center of the star to the surface where it has to drop to 0, because all field lines are taken in. If you calculate the magnetic pressure, or rather the force that comes from the pressure gradient, you will see that this is equally as large as the gravitational force. The magnetic force is equal to the gravitational force, or it can exceed it by up to orders of magnitude. So again, this star will not be stable. It will actually sort of expand again because of the magnetic pressure. So that's a problem as well. We have to deal with this as well. Magnetic fields must be reduced. Let's see what we can do. I said this already. B R squared is constant. That's because it's also called the frozen in flux. Magnetic field is attached to the gas. It's frozen in, as we say. Now let's go back to this term, the magnetic energy term that we had in our virial theorem. It read like B squared times R to the third. Now this B squared times R to the fourth is constant during collapse if we have a gas like the one we are now discussing. So this is not quite the same term, but almost. We actually see that this term varies like 1 over R as you compress a magnetic cloud. Let's go with 1 over R. But so does the potential energy, if you remember a few slides ago, also goes like 1 over R. So as long as you change this cloud, both go in concert. Magnetic pressure and the gravitational pressure both vary like 1 over R. So there's actually sort of nothing changing. If you compress a cloud, they're in balance or they're not in balance. Or in other words, if a cloud is stable, it stays stable, even if you compress it, because of the magnetic field pressure. If it's not stable, if it actually does collapse, it keeps collapsing because either gravitation is strong enough or the magnetic field is strong enough to collapse it or not, or to keep it stable. And it's always going on over R, so you have no change. So there we have a problem. If you have a magnetically supported cloud that is stable, it never collapses. So you have to do something. And now, by the way, you begin to see that what I said in one of my theses, clouds collapse because there's gravitation. They have to collapse everywhere. No, they don't. You see it here. And rotation is another factor. It's very difficult to make clouds collapse. So how do we do it? We do the same thing as before. We don't need a lot of physics for that. We just try to make the cloud collapse by violating the virial theorem. Now actually just requiring that potential energy is larger than magnetic energy. Always in absolute terms, because potential energy is negative. So let's just see what happens. Now we plug in the expressions we had a few slides ago. I don't want to go back to the formulae, but what you get is it's completely trivial. You just plug in, make this, plug it in here on the left side and the right side, and what you get, it's all for mass, is an expression that if the cloud mass is larger than this expression on the right-hand side, this cloud is not stable and it can collapse, but only then. And you see how easy this is. These are constants, gravitational constant here and another constant. And this is the magnetic flux. It says basically field strength times cross-section area. So easy. And if your cloud is larger than this expression, it can collapse. Otherwise, it cannot. It doesn't have to collapse, but it can. Because at the same time, you have to fulfill the Jeans criterion that we showed a bit before. You have to fulfill both of them. One is due to pressure, one is due to magnetic fields. So it can collapse. But the problem is, as we just saw, if the cloud is stable, it stays stable, so it doesn't collapse. We have to get to a situation where this is fulfilled. But it doesn't fulfill, it's not fulfilled automatically. We can wait as long as we want. So there's another important process. And that has, it's a process called ambipolar diffusion, and I'll just qualitatively show it. That is important to actually separate charges, the ionized part of a cloud, from the neutral part of the cloud. This is again our spherical cloud, very simple. We have magnetic fields, we have a few ions and electrons, and they are attached to the field lines. Now, we have neutral particles, and of course that's what I didn't say before. Of course, most of the cloud is neutral and not charged. Okay? Hydrogen molecules are neutral. So the neutrals can say, well, I don't care about the magnetic field because they don't react to magnetic fields. So they just do their job and collapse. The problem is that neutrals are also colliding with ions and electrons. And that breaks them each time. So you have, a neutral wants to go to the center of the cloud, collapse. But then it hits an ion and it's braked. And it continues and another ion stops it. And on and on and on. That's a frictional force. It's basically friction between particles. And what you get is not a collapse, but you get a slow contraction at constant velocity. So the neutrals slowly slide against the magnetic fields because they are stopped by the ions each time and the electrons. So you can actually, by this process, you can separate the charged particles from the neutrals because the charged particles want to stay with the magnetic field lines while the neutrals go across and condense here in the center. The magnetic fields are not, they don't want to follow the neutrals or, because they have tension. The magnetic field has tension and tries to withstand deformation. It wants to go back to a linear field line. And that's why, in the end, you have your ions more outside the cloud and your neutrals, which is by far the largest part of all particles, they move to the center. And eventually in the center, you accumulate so much mass while you do not accumulate magnetic fields that our magnetic criterion is fulfilled. So this process slowly goes into a direction that sort of reduces the magnetic field relative to the mass in the center until we can collapse the cloud. I hope this is still a bit clear. It's just comparing the magnetic pressure with the gravitational pull and considering collisions between neutrals and charged particles. That's what I said. Neutrals collide. The magnetic fields stay outside, and eventually we have a collapse. It looks very simple. Of course, it's a bit more complicated than that. But I don't want to go into all the little details. Now, how long does this process take? Again, this is a massive simplification. Nevertheless, the order of magnitude makes sense, and it's actually okay. Once we have a cloud that finally collapses, the magnetic field is not dominant anymore, so you can actually ignore it. Remember what we said, once a cloud collapses, it will keep collapsing, because the magnetic field, magnetic energy goes 1 over r, but so does the gravitational term. So once you have collapse, you don't need to fully consider the magnetic fields. Of course, they matter, they continue to matter, but in a simplification, we now just have gravitation. Also, we said, well, we exceeded the gene's mass, so the pressure is also becoming unimportant for a while. Now, that's an easy calculation to see how long it takes for a mass element to collapse. Let's just take, this is our spherical cloud. Let's take a mass element here, m, and the whole cloud has a mass of m. Actually, in gravitation, in a situation like this, spherical cloud, axisymmetric, and in fact spherically symmetric, if you have a mass at radius r, the gravitational attraction comes only from the mass inside the radius. The other mass outside has also components of gravitational force, but they all cancel. So we need to consider only the mass inside. Now we can make an equation and say the acceleration of this mass element is, of course, f over m. That's the second derivative of radius. It's basically acceleration, as you see here. And that is counteracted by the gravitational acceleration, which is this. It's Newton's law again, gm over r squared, divided by m, as you can see. This is a differential equation for r, and you can solve it and find the time it takes for this mass element to move from radius r to 0. So you check when it's there in the middle. And what you get is the so-called free fall time. And interestingly, this is full of constants. It's only a square root of 1 over the initial density of the cloud. Doesn't matter how big it is. Nothing matters here. It's only the density. That also means that any point at any location has the same time to collapse. Doesn't take longer for a mass element that's further away. You see, there's no R dependence. Radius doesn't matter. So this whole cloud collapses homologically into a point. And that's the free fall time that we get here. Now we can estimate this, again, going back to observations. What we find for a typical dense core, we're always considering, is about 200,000 years. Now we have a time scale. It takes 200,000 years, order of magnitude, to form a star. Of course, with lots of effects that we now ignore. So it can take longer, can be shorter. Okay, this is going a bit too far, but I want to show it anyway. There have been, a long time ago already, simulations or estimates how this collapse could take place. I'll show you two. This is a simulation. It's already quite complicated. You have a cloud with an initial condition and you contract it and let it collapse. This starts actually with a critical cloud that just fulfills the Jeans criterion, or the Bonn or Ebert criterion is almost the same. And you perturb it a little bit, you add a little bit more mass, and suddenly you fulfill the collapse criterion and it collapses. And this is a numerical calculation that shows you how it collapses. This is radius from the center, and that's the outside of the cloud, and you see the center of the cloud. It's a logarithmic scale, so you see a lot of distances here. This is sort of the size of a star. That out here we are at the surface of the cloud, 0.1 parsecs, right? So it's a huge range of distance. And you see on the y-axis the velocity shown negative as negative values because the velocity goes to 0. It's not expanding, it's a collapsing cloud. Doesn't matter really. And you see how the velocity profile forms here. You suddenly see velocity, non-zero velocity, and initially it was all at 0. And here the cloud collapses more and more in time until everywhere you have velocities, non-zero velocities, down to the very center of the cloud. And that's where the protostar eventually forms. Now that's one approach. I'll show you another one, which is not showing quite the same, but what you see here, eventually you have a centrally condensed cloud that has a lot of mass in the center. And the collapse takes place over the whole region. Now you can start with an initial condition that is actually one of these centrally condensed clouds. They're just becoming unstable. It's a different approach, but what you interestingly find in this case is that the collapse starts really in the very center where you have a lot of mass. And then there's more and more coming from larger and larger radii. This was developed by Xu in 1977. It's an analytical model. There's no simulation here. You can actually calculate this analytically. Collapse starts in the center. There's a wave moving away, and more and more mass will accrete. Now, why is there a wave? Initially, imagine in this situation here, you have collapsed the central part of the cloud to something looking like a star. But that means that this region here, the inner volume, is evacuated. There's no pressure anymore. Pressure is gone because material has condensed to a star. But then the next layer, just outside, suddenly feels like, oh, I have no pressure balance anymore. I just feel gravitation, and drops, right? If you move this floor here away in no time, just gone, then we end up in the cellar. If there is one, I don't know. That's the situation that every mass element feels. And then the next one breaks down. And the next layer says, well, I have no support anymore, so I also drop to the star. This is called an inside-out collapse of a molecular cloud. Very interesting model as well. And it has a lot of interesting properties that are useful for discussing star formation. Now, what happens really in the center region is a very complex thing. I'm only summarizing very briefly. So what we've done so far by violating the virial theorem, right? Magnetic fields and whatnot, pressure. We came from a prestellar core, as they're also called, or a dense core that has no star. We induced collapse somehow magically, right? By violating the virial theorem. But eventually we have this concentration of mass in the center, mass falling to the center. Now, what happens there? I mean, we cannot just. I mean, if we have this collapse going on, like with no counter force, we have a black hole at the end. So we have to stop this somehow. The problem is indeed that if you have enough mass in the center, the mass becomes optically thick to its own infrared radiation. It's of course warming up. You concentrate mass, and as you know, you compress gas, it warms up. Now, at some point, the infrared emission that the gas emits in the center will be reabsorbed by the next gas molecules, and then emitted again, but absorbed again. So this heats up the central part of the cloud. It warms up. And at some point, the pressure is enough to balance again and to make this core hydrostatic. So suddenly in the middle, you get a hydrostatic core. Not the whole cloud, but the central part. This is also called the first core. And typical sizes of this first core is 5 AU, so the distance from the Sun to Jupiter. These are not yet real stars, but they're quite big structures. And they contain only a small fraction of the mass that will eventually end up on the star, but they're already warm. Good, so we are somewhere here, the first core. In fact, the environment of the cloud is not really spherical. There's rotation. So, in fact, the cross-section, this is a rotating cloud. Along the z-axis, you have the rotation axis, I have radius here. These things look flattened, but I'm not going into more details here really for the moment. We'll see while the flattened structure is important. Good. Then we have further contraction of this hydrostatic core. There's more mass being added anyway. It contracts slowly, quasi-hydrostatically. But then it reaches a temperature where you have to dissociate hydrogen. The hydrogen molecules are dissociated into two H atoms, two hydrogen atoms. And that means that the energy that you add to the core is no longer used to heat the core, but it's used to dissociate hydrogen. So the core has a constant temperature at some point. It's just there's just mass being added from the infalling cloud. And that makes the cloud eventually unstable again, namely for the same reason. It becomes genes unstable again, because the mass is now so high for the given temperature that it can collapse again. There's a second collapse. And that then forms something like a star indeed. The structure is larger than our sun, but it looks a bit more like a star. That's the protostar eventually. And this whole process takes about 250,000 years. It's comparable to the free fall time we estimated before. Now, just a very simple consideration of energies again. We have all these terms, and let's look at them again. Let's go back to the initial cloud. Cloud is very extended. There's no star inside. These clouds don't have, we compared the terms, the energy terms, but let's now just look at the absolute value of these terms. There's not so much motion in these clouds. They're very cold, 10 K. And they're very extended. If a mass is far away from its center, it doesn't have potential energy. So the total potential energy of a cloud is actually not much. They're all small terms. But once you have collapsed to a protostar, then it looks different. The total energy of a protostar is again, of course, potential energy, thermal energy, and the energy that was put into dissociating molecules, and ionizing even. And then there's also the total energy that the star radiated in infrared, for example. You have to take that into account as well, which is luminosity times the time it took, the whole time there was luminosity. So that's the energy equation. And that has to add up. Because of energy conservation, this is going to be zero, because we started with zero energy, essentially, the top line, and we have energy conservation, so in the end we should still have this at a zero. Now, we also know from the virial theorem that 2 times the thermal energy is minus the potential energy. Put that in, there's something here that it's a bit of a problem, dissociation. We can show, there are arguments that show that this term is unimportant. So we can drop it. We have this simple equation. These two can be combined via the virial theorem. And we end up with an expression that says, well, then the radiation energy, radiative luminosity, should be an expression like Gm, the mass of the central star, times the accretion rate, that's the mass that comes in per second, divided by r. That's the luminosity of this object. And this is a luminosity. These objects are luminous like tens of solar luminosities. They're quite bright. They emit their radiation mostly in the infrared, but it can be quite bright. There's a lot of energy coming out of this. We talked about rotation and the collapsing cloud. Take this as the sphere that from which, at the surface of the sphere, there's more mass outside, but at this radius, mass breaks away and moves toward the center. That's this inside-out collapse. Let's assume that everything outside is still sort of stable, but at this radius, we evacuate the inside and mass falls toward the star. This radius will expand, will become bigger and bigger. Now, the individual mass elements will eventually fall somehow. The problem is this thing is rotating, so they cannot freely fall to the center because they have angular momentum. You remember the ice skater? You know, it's becoming very fast, and we cannot collapse to the center because the angular momentum, the centrifugal force becomes too big. The angular momentum is conserved. So what happens is that mass elements, for example, coming along the polar line, they don't have angular momentum relative to the axis, so they can fall freely. But these out here have angular momentum relative to the axis. Those mass elements from close to the equatorial plane. They cannot drop to the star anymore. They have to go somehow into an orbit motion. They indeed go in a motion that looks a bit like this, and you form a disk. You form at the equatorial plane, you collect all the mass that falls in, because much of the mass cannot really fall to the star directly because of angular momentum. So here you form the first formation of something looking like a disk, and we'll talk more about these disks in the next hour. There's a radius of the disk, and in fact that's we call this the centrifugal radius. This is the maximum radius that you form at a given time from this surface here that collapses. Because the further out you go with time, the more angular momentum you try to bring in, and the less it's possible that this mass ends up on the star. So you also make the disk larger and larger as you grow this rarefaction radius here, and you move outward. Good. I continue with this in the next lesson. I guess it's time to stop for the moment if you have questions or whatever, and of course you want to go into the break.